right, we'll get started. That was the quiz for Chapter 7. All right, so we just have just a few more weeks, together, okay? So this week we're covering Chapter 8. Next week we're covering Chapter 9. The week after that, I will just cover a few light topics from Chapter 12 and start to do a review, okay? Next week, during that week, so that's 2 weeks from now, we will meet twice that week, okay? Once on Tuesday, that will be when I'm covering the light topics from Chapter 12, and then again on Wednesday, all right? The Wednesday class is optional, but highly recommended. It's going to be a review session. I'm going to go over the final practice final exam and talk about stuff for the final exam. Okay, and then after that is the final exam itself. So what is that? So 1, 2, 3 weeks. 3 weeks. That's it. Yes.
How long is the review session?
3 hours. 3 hours. Okay. Everything is. All of our classes are 3 hours. Yeah. No.
Yeah, like extra credit.
Yeah.
No, it's not. I'm not allowed to do any kind of graded thing on that day. Okay, just because it's when you signed up, the class thing said Tuesday, so that thing meets on a Wednesday. So contractually, I'm not allowed to do that. Okay, so but I do encourage you to come. What's that? You want to tell?
For extra credit.
Okay.
You just said you give extra credit for like good deeds, and I think
We're good Samaritans in this class.
If I bring you a big bag, does that count? Can I just bring
No bribery here. Okay.
I don't want extra point.
Huh?
You can even take off a point.
Take off.
What?
All right. I don't. This is borderline weird. So we'll just leave it at that. Okay. Okay. But anyway, the final exam, very much heavy focus on chapters 8 and 9. I'd say about 70% of it will be chapters 8 and 9. Maybe about 10% will be from the. I'm going to basically in 2 weeks I'll go over some definitions from chapter 12. Okay, so maybe about 10% will be that, and then 20% will be questions from before the midterm. Okay, but I'd say about 70% comes from chapters 8 and 9. Yes.
So what about chapter 7?
Chapter 7. Okay, so chapter 7 forms the basis for chapters 8 and 9. Okay, so if you can do chapters 8 and 9, that means you can do chapter 7. All right. If you can't do chapter 7, you probably can't do chapters 8 and 9. All right.
Okay.
Okay. Because a lot of what we do today in chapter 8, you will see related to chapter 7. Okay. Well, actually, there are stuff explicitly from chapter 7, the confidence intervals, those things. Okay. Okay. So chapter 8. The topic is hypothesis testing, okay? So hypothesis testing involves setting up a pair of hypotheses, and then we use our data to see if one of those hypotheses is plausible. Okay. So in hypothesis testing, we set up hypotheses, okay? And then we use our data to see how plausible one of the hypotheses. To see how plausible one of the hypotheses. Okay. So the two hypotheses are called the null hypothesis and then we have the alternative hypothesis. Okay, H sub 0, H sub A. So HO, HA. And we always assume that the null hypothesis is true. We assume that H0 is true, okay, unless there is data that convinces us that H0 is not true. And in that case, we would reject the null hypothesis and conclude the alternative. Okay, so we assume that the null hypothesis, H0, is true unless there's data that convinces us that it's not true. And in that case, we reject the null and conclude that the alternative hypothesis is true. And on the other hand, if there is not enough data to convince us that the null is false, then what does that mean?
Assume the null is true.
Yeah, and we just continue to assume that it's true. It doesn't prove that it's true. We just continue to assume that it is. Okay. So this is all kind of abstract at this point. So let me just maybe use a real life example that seems, I don't know, a little bit more concrete. Alright, so think of a criminal court case. Criminal trial. And well, I don't. Is Cops still on the air? They don't show that.
From Spike.
Is it on Spike? They show reruns on Spike.
Yeah.
Okay. Well, what do they? If you've ever watched the show, what do they say at the end of every show? They say.
No one's proven guilty until.
Yeah. So it says
or
all
assumed
suspects
innocent until
are
proven guilty.
assumed innocent until proven guilty in a court of law, right? Okay. So that means in a criminal trial, we have a null hypothesis and an alternative hypothesis, okay? Alright, one is we assume that the null hypothesis is true. So what would this be in the criminal case? Yeah, the null hypothesis would be that the defendant is innocent. Okay, so we assume that the defendant is innocent unless there is evidence convincing us otherwise. What would the alternative be? The defendant is guilty. Okay. So we assume and it's the prosecution's job to present evidence that this is not true. So if the prosecution does not have enough evidence, the judge will just dismiss the case. Okay? If they say, oh, that's not enough evidence, they just dismiss the case. All right? But then maybe they present a bunch of evidence, and then it's up to the jury or the judge or whoever's presiding what the outcome is. Yes, okay. So it might be, you know, we assume that you are innocent, okay? But if you were innocent, why did you have all these drugs in your apartment, okay? I don't know, they just somehow showed up, okay? If that's the case, why was your name, you know, in all of these transactions? And why did you keep calling this person that is a known drug dealer, okay? Huh? It's just, I had no idea he was dealing drugs or something, you know? So, they present all of these things, and they say, okay, well, you know, if we assumed you were innocent, how can you explain all of these pieces of evidence, okay? So basically, evidence is presented. Okay, and then we'll say, you know, if you were innocent, how do you explain such and such and such? Okay, so someone might say, oh, I just happened to be at the wrong place at the wrong time, and it makes me look like I'm guilty. But that was just weird, you know. The drugs ended up at my apartment because the UPS guy came and it was a misdelivered package. I don't know. Okay, so maybe that's true, or we could say, you know, that doesn't seem very plausible. And if there's enough evidence, we would say, I can no longer reasonably believe that you are actually innocent, okay? And if that's the case, then the jury concludes that the defendant is guilty. Okay, so if there's enough evidence, we would reject the null and conclude the alternative. Okay? reject H0, H0 being the idea that the defendant is guilty, or the defendant is innocent, okay? They would reject that idea and conclude on the other hand, let's say there wasn't a ton of evidence. Okay, they say, oh, we think you murdered this person. And then you say, well, why do you think that? There was a witness and they said they saw a man with dark hair who was around your height, 5'10". And they say, is that all you have? You go, yep, that's all we got. We think you're guilty. Well, in that case, you would say, well, if we assume that the defendant is innocent, is it quite possible that someone else was 5'10" and had dark hair? Yes, that seems reasonable. So it's not enough to convince us that the defendant is guilty. Okay. All right. Okay. But you know, maybe there was something a lot more convincing. Okay, they say, you know, we think you are guilty of the murder. Yeah, what do you think that? Okay, well, we have these security camera, and it shows a man with a giant, you know, this very unique tattoo all over your back, and you have the exact same tattoo that shows up in this video feed. How do you explain that? You know, the guy says, well, I'm innocent, and there just happens to be someone else in the world who looks exactly like me with this exact same tattoo. Is that possible? It's possible, but it seems highly unlikely, okay? And if that were the evidence, it would probably be enough to convince someone of guilt, okay? Does that make sense? Okay, so we are going to do the same type of thing, but with statistics and numbers and calculations, okay? So it's just as exciting as your favorite Law and Order show, but maybe not. Okay. Are court procedural shows still on the air?
Yeah,
Just what? No, not Judge Judy, but like those dramas, like Law and Order. Is that still on? They still have like season 853 or something. Okay. Okay. So in statistics, we do something similar. Okay. Except we use, we're going to use numbers and symbols. But the general idea is that our null hypothesis will state that the proportion of our population is equal to some number. Okay, so let me just say, for example, I'm just going to use 50%. Okay, so the null hypothesis might be something that the proportion is equal to 50%. And along with this, we generally don't write all of this out, but as I'm explaining this, I'm going to say is that the null hypothesis would say that any discrepancies in our data is a result of randomness. Okay. And the alternative might be that P doesn't equal 50% or is something else, okay? And this would say any discrepancies in our data Alright, let's say we decide to play a silly gambling game, okay? How silly are we talking? Okay. Maybe not that silly. Alright. Gambling game. Alright. It's very simple. I'm going to flip a coin, and if it lands heads, you win money. If it lands tails, you lose money. Okay? Fair enough? How often should you win? 50% of the time. Okay, so gambling game. You flip a coin. If it lands heads, we win. If it lands tails, we lose. Okay, we should win. Okay, but if we play the game a bunch of times, are we going to win exactly 50% of the time? No, because there's a random chance, right? And that's why people gamble, because
They don't like the money.
huh?
They don't like the money.
They don't like the money, yeah. They like burning it. No. Well, there's the chance that you might win, okay, or you might lose, and it can be exciting. All right. So, well, anyway, let's say there's some casino that offers this, okay, and I decide to go play. All right. And then this is best odds in the house, right? Exact even money, things like that. Okay. So let's say I play the game 10 times. Okay. And let's say I win 70% of the games. Okay. Is that a good day? It's pretty good, right? Alright. So the casino, he's got the casino manager or pit boss, he comes out and he says, "Hey, I think you're cheating." I go, "What?" What do you mean? He's like, "You should win only 50% of the time." Why I got lucky. I won 70% of my games. All right. He says, "No, you should win only 50% of the time." So what do I say? Huh?
Then it's not 50%.
Yeah, he's saying I should be winning only 50% of the time, but I won 70% of the time.
Then the game isn't 50-50.
So he says I'm cheating.
No, but he has to proof against you
Why doesn't he have any proof?
because it's a game chance, yeah, it doesn't matter.
So, my argument is, no, I just happen to be lucky.
Result is different.
I'm playing fair, yeah, and that the discrepancy, I want 70%, which is different from what we might expect 50%. I want more, but that's just a result of randomness. Okay? So my defense, so I won 70% of the game. Casino accuses me of cheating. Okay. And my defense? No, I'm not cheating. No, I'm not cheating. I won 70% of the games just from random luck. Can we actually find the probability that I win 70% of the games out of 10 games?
Yes.
Yeah? How do we do that? Later on we'll do z-score, but in this example, it's not a z-score problem. It's a binomial problem. It's a binomial problem, right? We have an n, a p, and an x. Except the x doesn't look like an x. Alright? I'm playing a game 10 times. Every time I play the game, I've got a 50% chance of winning. And I'm looking to see what's the probability that I win 70% of games, or 7 games out of 10. Is that okay? Alright, so according to your binomial table, what's the probability of winning 7 games out of 10? N is 10, P is 0.5, X is 7. That probability is what's that? 0.117?
Yeah.
Okay. 0.117. So that means anybody who's playing the game perfectly fair, they're not cheating, they're not doing anything wrong, that they have a 11.7% probability, or about a 12% probability of winning 7 games out of 10 just from random luck alone. Does that make sense? Okay. So that means if the casino is accusing me, then that of cheating, then that means they would actually also be accusing about 12% of all players who are playing fairly, just because they won 7 games out of 10. Does that seem like a lot of people to be accusing of cheating? Seems like a lot of people to be accusing of cheating, right? And if they accused me of cheating when I won 7 games, they would certainly accuse me of cheating if I won 8 of the games, right? Alright, so what's the probability of getting 8 games? What's that?
Yeah, 4.4.
0.044?
Yeah.
Okay, x is 8. And what about x equals 9 and x equals 10?
0.010.
What's that?
0.010.
010 and
0.001.
001. Okay, so if they accuse me of winning 7 games, they would also accuse me if I won 8, 9, or 10. So they would be accusing a total of, I don't know what this is. So this says that 17.2% of fair players my defense is that I'm not cheating. I won 70% of the games from random luck alone. And I say, if you do the math, about 17% of all players who play this game will win 70% or more of the time. Okay? Does that sound good? Okay. And so 17% sounds like a lot of players to be accusing of cheating, a lot of fair, honest players. So the casino probably would not want to accuse 17% of their players of cheating if this happens just for random luck. Okay. Does that sound good? Okay. All right. On the other hand, okay, so I say, go away. I'm not cheating, all right? Don't you know who I am? All right. Okay, so let's say I keep playing, all right? I feel good, I keep playing. Okay. Now I've played 100 games. I've played 100 games. And lo and behold, this time, I've won, I win 70% of the games. Okay? So the casino manager, he's angry again. He says, I know you're cheating now. I got you. Okay? So the casino accuses me of cheating. And what do I say? I go
17.2%.
Okay. I said, I thought we just did this. Last time I won 70% of my games. And we found out that I wasn't, you didn't have enough proof to say that I was cheating, okay? I'm still only winning 70% of my games. Do you think I'm cheating?
Yeah.
Maybe. Huh? Or am I really lucky?
No,
What's
man.
going on?
Can't be that lucky.
Can't be that lucky?
You're outsmarting
So
us.
it was 70% over there, and it's still 70% over here. What's going on?
But when you play 10 games, winning 7 out of 10 isn't that big of a deal. But winning 70 out of 100 is a lot more than average, more than the probability.
All right. Okay, I like where we're going here. Okay.
What if some other guy lost 30 out of 100 games? Then it's
Yeah, the casino would say, I accuse you of cheating, but the wrong way. They probably won't say that, okay? So we played a game 10 times, winning 7 out of 10 games. That's not that weird, okay? But now we've played 100 games, and here I've won 70 out of 100. That seems a lot harder to believe that happened just from random luck alone, okay? So we're going to ask the question. So again, my defense is, I'm just really lucky, okay? I'm just really lucky, okay? Okay, so can we find out the probability of winning 70% or more games
No.
from random luck alone?
Yes.
Okay, so if I am playing fair, okay, meaning if I'm playing fair, what's my probability of winning? 0.5, right? I'm flipping, it's a coin flip game, right? So if I'm playing fair, the probability that I'm winning is 0.5. So if I'm playing fair, what is the probability that out of 100 games, I win 70% or more of the games? Do we know how to answer this question?
0 plus.
Huh? Yes, we should. We should, okay? Because you just had a quiz on this. Alright? This is a central limit theorem problem, okay? Here I have a sample. What is the size of my sample? 100 games, okay? What is the proportion in the population if I'm playing fair?
0.5.
P is 0.5, okay? And I'm asking, what's the probability that a random sample of 100 produces what? 70% or more, okay? So we're asking, what is the probability that P hat is greater than or equal to 0.7? Can we do this?
Yes.
Okay, so take a minute, take a couple minutes. Let's see if you can answer this question.
Yeah, and we need to figure out what the P hat are. So the P is 0.5 plus the P hat. That's what I'm stuck on.
What's your standard error?
Okay, so then you have to do, but no, hat is a 0.7, P hat is a
P is 0.5. Right? More than 70.
Okay, then if it is 0.7, then you would have to do 0.7 minus 0.5 divided by 1.
Yeah, that's
I got
you're
negative
totally doing it right.
Oh, yeah?
Yeah, yeah.
Which is fine.
Press,
Because
press.
then you
Because a
want
lot of students want to get that
Yeah.
handout. Because you went here, right?
Yeah.
Yeah.
It's .99991 minus that, right?
Yeah.
All right. How are we doing? So we got a standard error?
I got a very low number.
Yeah, okay, what's our standard error? Standard error is 0.5 times 0.5 over 100, and after taking the square root I get 0.05?
Yep.
Yeah.
Is that what we got? Okay. What's my z-score? 0.7 minus 0.5 divided by 0.05. I'm getting a z-score of 4.0. Is that what we got?
Yeah.
Okay. And we go to our z-table, and what do we see? We don't see 4 on the regular part, okay? Oops. We have to look in this little corner here, okay? All right. We look in the little corner. We see z is 4.0. You guys see that?
Yes.
Okay. And that means, you know, if you get like 4.1 or 4.2, we don't have an exact number, but it means it's going to be in between the numbers for 4.0 and 4.5. So anyway, this says that, well, it says I'm 4 standard deviations away. Is that a lot?
Yeah.
That's a lot, right? It's off of our charts, okay? It's off the charts. So,
The charts.
yeah. All right. So we're at 4 standard deviations away, and that says we would have 0.9999683, okay? Which means over here I would have 0.0000317.
Yeah.
Okay?
Totally pulled it off.
So what does that mean? That means if I'm playing fair, so we're playing the game, right? What's the probability that out of 100 games I win 70% or more of the games by random chance? It happens about 0.0000317 of the time, okay? That's about, this is like 3 in 100,000, okay? So in 100,000 people, this might happen 3 times, okay? So,
Probably 1 in a million.
yeah, so the casino can say, okay, I guess you were one of those lucky 3 in 100,000 people. Or they can say, I think you're cheating, get out of here. Okay? So what do you think? Yeah, what do you think they would do? They would probably say, don't come here ever again. Okay? You're not allowed to play. Play at the game. Yeah, they take our picture.
It really
and,
sounds like
whatever.
the movie 21.
Huh? Yeah, they do, you know. So if they think, you know, if they can prove that you're cheating, you're in big trouble. But if they just think you're cheating, they might just say, don't come back again. Okay? So, but is it possible that I was just really, really, really lucky?
Yeah.
It is possible, okay? It is possible that I was one of the 3 in 100,000 people. But the casino is willing to say that is so small, or so small of it actually happening, that we're willing to ignore that and just conclude that someone is cheating here. Okay?
I have a question for the Z.
Yeah.
Why would it be 0.7 minus 0.5 instead of 0.5 minus 0.7? Is it because the p hat isn't
Yeah, it's p hat minus p. It's if the null hypothesis were true, what are we expecting to get? We're expecting to get a proportion of 0.5. So that we're going to put that in our mean as our center.
How would you get 0.0000?
I did 1 minus the 0.9999683. Yes. Our p is 0.5, which is what we are expecting. So yes, in our sampling distribution, our mean is 0.5. Okay, so let me write that explanation out. 100 games fairly, probability of winning 70 or more games is only 0.000317. Okay. The casino can say, okay, you got lucky. You got really lucky. We don't want to accuse you of cheating. Or say this is too rare of an occurrence so we do not believe and they will probably conclude this. Yes.
If I win if I win like 30 out of 100 times, do I have a case against the casino?
Yeah, you could say,
It's not fair.
yeah, you could say, I have evidence that the casino is rigging the game against me or something. Yeah.
Flipping a coin.
Flipping a coin, yeah, somehow.
Sue them for mental,
Okay. Well, I mean, so that's why, you know, like in Vegas, they have the Nevada Gaming Commission that goes through and
make
checks,
sure each game is
checks to
fair.
make sure that all the games are fair and stuff. Alright, does that example make sense? Both of the examples? Okay, so in one example, I won 70% of my games out of 10 games. And the conclusion was, that's not enough evidence to say I'm cheating. In the other example, I won 70% of my games out of 100 games. And it turned out that that was so unlikely to happen by random chance that we concluded that I was cheating. Okay? So I'm going to do the second example again, but this time a little bit more symbolically, the way that that you might do a homework problem. Okay? Because here I did, you know, I wrote out a lot of words and stuff, which I think is good to help us understand. But when you do a problem, you probably don't want to write all of that stuff out. Okay? So, so the problem would probably be written like this, okay? A coin has a 50% chance of landing heads. guys ever watch Vsauce on YouTube? And he had a video on randomness, which was pretty good. Okay, and he talks about coin flips and how there's robots that can flip coins with such precision that it will know whether it lands heads or tails, which is kind of neat. Okay, but anyway, so this is what we've got going on. So in our case, our hypotheses would be our null hypothesis is that P is equal to 0.5, and our alternative is that P is not 0.5. Okay. Our data is n is equal to 100 coin flips, and our sample proportion is 70 over 100 equal to 0.7. So here's our hypotheses, here's the data that we have. Then we do something called finding our test statistic. The test statistic involves finding the standard error and then a z-score, at least for these problems, okay? So our standard error would be, and notice I'm using P and not P hat for a standard error. Is everything so far so good? Okay, our z-score is going to be area is 0.000031 because this was 0.99996. Yeah, I'm doing the exact same problem, just symbolically, okay? All right, without all of the words. We have a question. So here we're doing z-scores, okay? And that's because when we had only a sample of size 10, we did not meet the large sample condition. Okay, remember, to use the normal model, we have to meet those three conditions: large, big population, large sample, random things. Okay, we didn't meet the large sample condition. In our case, yeah, you have to use the binomial in that situation. Okay, but here we meet the large sample condition. So this is what we have. Okay. I'm going to just introduce a new concept right here, and I will define it in more detail in a moment here. Okay. The p-value. Okay. The p-value is basically my tail area, okay? Or it's going to be 2 times my tail area. And it has to do with what's written in the alternative hypothesis, okay? So right now my alternative hypothesis has a not equal sign. When it has a not equal sign, the p-value will be 2 times the tail area. Sometimes the alternative can have a greater than or a less than, and in that case your p-value will be either the tail area or 1 minus the tail area. Okay. So I will explain all of this, or I'll define all of this clearly, but just go along with me when I say the p-value is going to be 2 times my tail area okay, and it's because the alternative has a not equal sign in it. So my p-value is going to be equal to 0.0000634. Keeps buzzing.
Is it our Facebook group?
No. It's my birthday, so the people are.
Oh,
Happy birthday!
Let's sing. Sing. 1, 2, 3. Happy birthday to you. Happy birthday to you. Happy birthday, dear Miles. Happy birthday to you. And many more.
Okay. Well, thank you. That was very lovely.
25.
I did not turn 25.
20.
This is we'll play a game. You can try to guess my
It might be
age.
the 33-0.
All right. So anyway, what?
What's the probability?
Yeah, the probability distribution, right? This is the actual age. I don't know. All right.
34.
So so my p-value is 0.000634. Okay, and so at this point,
31.
I'm going to tell you that my p-value is small, and so that will lead me to reject the null hypothesis. Okay, so just take my word for it. So our p-value is small. Okay. So we reject the null hypothesis, and we conclude that HA is true. Say we have evidence that P is not equal 0.5, or in other words, we have evidence yes.
At which point, when the value is small enough, do we get to reject it?
Yes, I will explain that in just a moment, okay? But I want you guys to write all of this down. Okay, is this all right? So, I'm going to erase this. Let me Okay, why don't we take a break? We'll take a